So welcome to this quantum information and coherence talk. For those like at least few students who are joining for the first time, this is a very tutorial and informal level talk covering broad areas in quantum information and coherence. And today we have Professor Omar S. Magana-Loaiza. Did I say it correctly? Okay.
Yeah.
Excellent. From Louisiana State University. So just a quick intro to Omar. So Omar has his bachelor's from Mexican University, and then he did his doctoral from PhD from University of Rochester. And he got his degree in 2016, and that's in optics. I did my thing is the same place, although we didn't overlap. I think just missed, right? Almost just missed. Probably you joined 1 year later than I kind of.
I think so. Yes.
Okay, and so after finishing his PhD in optics, he became a research associate at NIST Boulder. After that, in 2018, he joined Louisiana State University, where he's currently an associate professor of physics and leader of the experimental quantum photonics group. His research he focuses mostly on novel properties of light and their potential for quantum technologies. He has received this early career program from Army Research Office, and his academic career was also highlighted in Physics Today. And what he's talking about today is multiphoton quantum imaging. Well, he has changed his title a little bit, so that's multiphoton quantum technologies. That is even bigger and hopefully better. So Omar, over to you.
Thanks, Anand. Thanks for giving me the opportunity to tell you a little bit about our research. As you just mentioned, I changed the title a little bit, and the goal is to use the first part of my presentation to describe multiphoton interactions. And then in the second part, I want to describe how these interactions can be used to do something useful. And I will just describe imaging. So the research that I will be presenting was actually performed in collaboration with members from my team. Just to give you more information about what we do. In my lab, this is a quantum photonics lab, and we work on multiple research fields. We do quantum communication. We are also interested in quantum imaging and metrology. We do quantum plasmonics, and we are also working on quantum information processing using waveguides. And all of them are related to multiphoton, and this is one of the topics of my talk. Well, why do we want multiphoton systems for quantum technologies? In general, I will say that, well, in general, if you have multiple particles, let's say multiple photons, they can interact in many different ways. And the more particles you have, more interactions you can use for developing technologies. And the question is, how do you access to these interactions? Well, one way is by using specific detection schemes. And just to give you an idea of the potential of multiphoton systems, imagine that you have 3 photons and they can interact through 5 paths. So what you will have is actually 30 different interactions or possibilities. So here we're using this red spot to indicate like an interaction, so you can consider this as a multiport device. So if you increase the number of particles to 6, and then if you have 10 different paths, then you can have up to 7,000 different interactions. And the nice thing is that you can use all these interactions to do something helpful. And what I will show you today is that we were exploring some multiphoton interactions. Yes, excuse. Oh, okay. Sorry. So you have multiple interactions, and I will just show you how you can use these interactions to develop robust quantum technologies. And specifically, I'm interested today in describing quantum imaging. So one of the what you need if you want to work on this field is you need to have a bright source with multiple photons. And we have been developing some of these sources over the last 5-6 years. So for example, here we have, I'm just showing that we have the capability to create wave packets with different number of particles. So these are the unit photon number distributions. And each of these wave packets can have different quantum statistics that are measured by the Mandel parameter, so we can control that. We know how to do that. We can also engineer or control entanglement in these multiphoton systems. We have been working also really hard to make these wave packets indistinguishable, and then we have implemented quantum interference experiments with that. So more recently, we generated spatial modes of light with different photon statistics at different spatial distributions, and we have been using that for imaging. And what I will just describe is how some of these schemes for generation have been used to develop like more robust quantum technologies. Another important part for our research is photon-number-resolving detection. So in quantum mechanics, in quantum optics, we all use, or most of the time, we use clique detectors. And what these clique detectors tell you is basically whether or not you have a photon. You don't know the number of photons that you have. You just know that you detected live. If you use photon-number-resolving detection, you can actually infer the number of particles that illuminated your detector. For example, you should be able to tell here that you have 3 particles. Here you should be able to tell, oh, here I measured 2 particles or 1 particle. And we use that information for multiple applications, for example, to engineer multi-photon quantum systems. We also use that for sensing and metrology, as indicated in this diagram. We are also interested in like matter interactions in metallic nanostructures. I will briefly describe this work. And then we have been using this photon number resolving detection for super resolution imaging, as indicated in this diagram. So to study these interactions, we will use a plasmonic platform. And let me very briefly tell you what a plasmonic wave is. So a plasmonic wave is an optical wave that you can excite in the surface of a metal. So here we are assuming that we have gold, and then here maybe we have free space or a dielectric. And then the plasmon is produced by the coupling of electromagnetic waves or photons through the electrical charges in the metal. So it's a quasi-particle. And in the limit of many, let's say, electrons, so this quasi-particle or this plasmon behaves as a boson in general. You can generate these plasmonic fields in metallic surfaces, but also if you have like a small particles, metallic particles, you can induce what we call localized plasmons. So what I will describe today is more related with these superficial waves. And we use these superficial waves to understand some of these multi-particle interactions. So we do that in plasmonic platforms. And eventually the effects that we observe in these platforms, we use those to develop robust technologies for quantum imaging. So let me tell you one nice thing about surface plasmons. So if you just have something like as simple as a nanoslit, something like that, it has been demonstrated actually by us that this nanoslit can actually act as a relatively complex network. So for example, this device can be mapped into what people call a treater, and a treater is just a 3 input and 3 output device. The advantage is that if you do this through plasmonic platforms, this is very easy. It's just a nanoslit. And then you can add other things like gratings and basically gratings or phase shifters to make this a little bit more complicated or to induce a higher degree of control. But in general, this implementation is actually really useful. And that's how we started working on this, because we thought that, well, this might be a platform for quantum circuits, for example. And one of the things that we realized when we were analyzing these platforms is that in general, people used to believe that these kind of nanostructures preserve coherence and entanglement and then quantum statistics. In the beginning, we believed that, but then after thinking, you can imagine that depending on what you inject here, you will get different outcomes. And if you get different outcomes, your statistics will change. And we decided to study that first. We say, okay, let's see what's going on. If we measure the statistics, we will understand these interactions a little bit better. And just to remind you about statistics, here I'm considering three sources of light. So I'm considering thermal light, I'm considering coherent light, and I'm considering single photon emitters. So these are like three different kinds of light, and they have different statistics. For example, if we measure the G2 or the Mandel parameter for thermal photons, we'll get one number. If we measure G2 or the Mandel parameter for coherent photons, then we'll get one value, and the same for single photon emitters. So what I will show you is that if you inject a multiphoton system on a plasmonic platform, you can actually tweak these statistics, and you can start with one particular kind of light and end up with a different one. So this is what we did back in 2021. So we prepare our multiphoton sources. So here we have two sources, and then we have different polarizations. And it turns out that these plasmonic platforms excites plasmons only when the photons have a horizontal polarization. In this case, and here what I mean is horizontal with respect to this nanostructure. So if the polarization is oscillating in this direction, so these photons will be converted into plasmon and they will travel in the surface. So here we're representing these plasmons through these lines here with different trajectories. So, and I'm also representing the plasmon with these clouds. So for example, here I'm illuminating this slit with diagonal polarization. The vertical component of the field will just pass through it, like following a trajectory like the green line. Let's say if this is our detector, we'll have the vertical component just passing through. And then the horizontal part will excite this cloud. And then now the plasmons, or let's say the photons, will be able to move inside in all these different trajectories. And just like before, just like in one of the first slides that I show here, we have multiple inputs. We have different sources. And then with the plasmonic field, we can induce different interaction paths. And if we have multiple interaction paths, these two sources can interfere in different ways, and they will change the statistics. And this is what we're showing here. Since this is an old paper, I won't spend too much time describing this, but here what I'm showing is that if the source is thermal, just like sunlight, or for example, one of the modes in spontaneous parametric down conversion, if you just inject one of the modes, you will get thermal light, and the degree of coherence will be close to 2. If the polarization is vertical, let's say for one of the sources, then you won't excite any plasmon, so the light will just pass through, and you won't have any modification of the statistics. But then if you rotate polarization, let's say to 45 degrees or 30, you will excite some plasmonic modes here. You will induce these exotic trajectories. And then you will have more sophisticated interactions that will change the statistics. And if you change the statistics, you will change the degree of second order coherence. Then you will have something in between. And if you keep changing the polarization of the input field, you can modulate the thermal fluctuations of the field. Or if you go from this point to this point, you can thermalize your field. And here we're just showing that the photon number distribution of the transmitted beam here. And as you can see, the G2 changes for different polarization angles. Here we have 0 degrees, so we have thermal. And then here we have partially coherent, but in the photon number distribution. And then we have a G2 close to 1.5. So when we publish that,
Omar, just a quick question.
yeah.
On the previous slide, yeah, this one. So here the interference is between the plasmonic paths, different plasmonic paths from source 1, but not between source 1 and source 2. Is that correct?
In the paper we have both experiments. So yeah, so in the article we discuss both cases. Yeah, but the simplest situation that you will have is if you have just one particle, then the photon will interfere with the plasmon. That's the simplest picture. And as you keep increasing more particles or more sources, then this becomes more complicated. But the point that I want to make is that the statistics are not preserved as people thought before. So the statistics actually change.
Okay. No, I was thinking from the perspective that there's no coherence between source 1 and source 2. So to begin with, right? And so
to begin with, yeah.
So the different plasmonic paths from source 1 and source 2, I mean, they will have nothing that will ensure that they interfere. Is that correct?
Well, yeah, that's an interesting question. So in the beginning, they are independent and they won't interfere. But then in the paper, we show that we can use these plasmonic excitations to change the distinguishability between these two sources. And that modification will actually induce an interaction between the two sources.
I see.
Yeah.
I see. So here there is no, or is there a sense of like nonlinear generation and annihilation of particles that induces that kind of coherence or interaction?
No, in this case, everything is linear. So gold is actually non-linear, can be non-linear, but in this case, our input field is so weak that everything remains linear.
Okay.
Yeah, but gold is a Chi3 material. So if you pump it hard, really hard, then you can induce non-linearities. But that's not the case in our paper, because even though we are using multiphoton systems, they are weak still. So
Okay.
induce non-linearity. Yeah. Yeah. So I mean, just because I mean, I just try to summarize our work, but the point is that after we published this, we said, okay, the statistics actually change. And if the statistics actually change, is because you have many interactions like the interactions that I described in the beginning. And we recently decided to study that. And we did a very similar experiment, a little bit more complicated, but still we have two plasmonic, we have a double slit nanostructure. And then what we did is same thing. In this case, we're only using one source. And then each of the multiphoton subsystems in this source excite a plasmonic field. For example, the 3-photon component of the source will excite a plasmonic field, let's say with 3 particles, assuming that we don't have losses, but we have losses. And same if we have a vacuum. So in this case, this wave packet will excite what we call a vacuum plasmon. So then we induce these plasmonic interactions, and then we measure each of the subsystems using photon-number-resolving detection. And just to make sure what we have here. So in this case, we have just a thermal beam of light, classical thermal beam of light. And as you can see here, the G2 is close to 2. I mean, it's almost thermal. And what we have here is the number of photons detected by, let's say, the arm by detector 1. And then here we have something similar for detector 2. And this is the joint photon number distribution, basically for thermal light. So this looks very, very coherent. And the difference with respect to the previous experiment is that now we will take a look to each of the elements in this joint photon number distribution. And we will see that each of these subsystems, we call them subsystems, they behave in a very specific way. Just to describe the system, based on the information that I gave you, it's only when we excite or when we illuminate this plasmonic sample with horizontal polarization that we excite plasmons. So in the horizontal mode, we have photons and we have plasmons. And in the vertical part, we only have photons. And then we have like a hybrid system between photons and plasmons. But still, the statistic is just this. So in a minute, I will just describe the different dynamics shown by each subsystem in the thermal field that we are using. So this is our experimental setup. We have a thermal multiphoton source. And then here we have a pre-selection port. And I will just explain you why, but here we just pre-select on vacuum. I will provide more information. And then the other part of the beam illuminates the sample, and we are only illuminating one of the slits. And as I just described, depending on the polarization is the strength of the plasmonic field that we excite. Then part of the light is transmitted, and then we have 2 ports, 2 detectors. And here we project onto N1, and here we project onto N2. And then in the end, we will correlate the 3 detectors to study this plasmonic dynamics. So this, it sounds a little bit weird, but one of the things that we wanted to do in our experiment is to explore the vacuum dynamics of this subsystem. So we use a technique recently introduced by Pittman, and they call it zero photon subtraction. So photon subtraction has been known for a while, and recently they introduced zero photon subtraction. And what that in summary, what that scheme does is it increases your probability of observing the vacuum. So here I have a table. If you do not condition your detection to this port, you still see most of the time vacuum, but the contribution from vacuum is relatively small. Even though that's the most prominent contribution, it's relatively small. And then your probabilities of observing 1, 2, or 3 particles decrease. This is if you don't condition or if you don't do vacuum subtraction or zero photon subtraction. If you condition your detection scheme to the vacuum, then you increase your chances of getting the vacuum. In this case, we were able to observe the vacuum or vacuum events like 82% of the time. And then we also change the probabilities of observing 1s, 2s, and 3s. And in a minute, I will explain why we did that. So just like in the previous experiment, if the polarization of the input field is vertical, we don't create or we don't excite any plasmon. So we will just get the diffraction pattern from this slit, and you have something like Gaussian. If you excite some plasmons, then a part of the beam, part of the photon will travel through the second slit, through these plasmonic fields. And then we'll have the interference between a photon and a plasmon, and you will see something like that. So you see some fringes. And if you change your polarization to almost to horizontal, then your visibility increases. Oops, let me see what I did here. Okay. So your visibility increases, just like in this case. And one of the things that we know, I think that it's obvious, uh, but we emphasize that in our paper, is that here what we have is basically intensity, and intensity is actually produced by many multiphoton effects. So here we have interference between, let's say we have single photon interference, we have two photon interference, and then we have higher order interference. So the intensity comes from multiphoton interference. And this is what we wanted to explore here. We wanted to understand these multiphoton interference that lead to these macroscopic interference patterns. And we can do that by implementing projective measurements. So what we did, we were interested in, as I mentioned it before, we were interested in understanding the vacuum dynamics. So we consider a case in which the plasmonic angle is 30 degrees, so it's something like that. And then we just measure the probabilities of detecting the vacuum. And we saw that the interference pattern is different with respect to this one, as you can see. And then if we increase the chances of producing plasmon, if we rotate polarization to horizontal, just like that, and we just measure the vacuum dynamics, we measure something like that. So this is theory and this is experiment. So here, these interference patterns were produced by the vacuum fluctuations of the field. And in this case, these vacuum fluctuations of the field excite vacuum plasmon, and they produce these interference patterns. So another thing that we analyze, same for this case, is what happens when we project onto a multi-particle subsystem, and we project onto this 4-particle system. What we saw is that now we get an interference pattern that is very similar to the blue one here, but one can increase the visibility of this interference pattern by post-selecting or by measuring higher photon numbers. For example, if you measure 6, you improve the visibility. If you measure 8, you almost get perfect visibility. And here, when we saw that, we say, well, that's interesting, because you start with an interference pattern that is macroscopic, that is classic, and then by implementing these projective measurements, you can increase the visibility. And we thought that maybe there was some kind of coherence, quantum coherence associated to this effect. So what we did is we measured the degree of coherence for different multiphoton subsystems. So for example, each of, let's say, this point here that you see here. Well,
Omar, just a quick question.
Uh-huh.
In the last slide, the fringe period is not changing as a function of n. I mean,
The only thing that changes is the visibility.
so typically, would you not expect fringe period to change with the number of particles involved, sort kind of changing? I mean, there's no reason to expect why should they be exactly the same. So, do you have any quick intuition on that?
Well, in the theory, this is not described because the theory is a little bit annoying. It's a little bit long, but it's reported in the paper. So what we get is something that it's close to the interference pattern to the end. And when you go to the end, then you have higher harmonics. So actually, there are higher harmonics here. It's just that you will have to isolate like the main frequencies to see these additional harmonics. But yeah, but basically this interference pattern is proportional to this to the end. And if in this case you post-select on 8, then you have a cosine to the 8 plus other things.
Okay. And the probabilities that's listed on the y-axis, let's say for n1 equal to 4 and n1 equal to 6. I mean, these numbers are in the same, there's a proportionality, or these numbers are, we can compare in an absolute sense?
Yes. They are actually proportional to this joint photon number distribution. So, for example, if you measure 8, so your probability is very small in comparison to, let's say, this or any other element. So those
Okay.
probabilities that you saw are proportional to this unit photon number distribution for a thermal light beam.
Okay.
Yeah. Yeah. So so as you increase n, then your probabilities of observing that event drop dramatically. But as you can see here, most of the time, and also this is in agreement with the joint photon number distribution, most of the time you will see the vacuum. So if you want to get this back, the classical one, then what you have to do is basically add all the quantum subsystems. You will have to add C to D, to E, to F, to the other contributions, and then you will get back the blue, in the interference pattern in blue.
Okay.
So actually, this in
Yes. So
There's
how
one
are
more
you
question.
getting? Yes. How are you getting the probability of vacuum fluctuation? I mean, with respect to what, or I mean, how the vacuum events are calculated?
Well, that's an interesting question. So, and this is related with this zero photon subtraction. So to explore the vacuum dynamics, we wanted to make sure that the vacuum that we were measuring really comes from the vacuum and not maybe from a photon that was lost and induce a vacuum, right? Because there are multiple ways in which you can get vacuum. So you can get a vacuum just if you don't see any event, but obviously that won't give you any signal that oscillates or anything. So you can get vacuum if you have one particle and then you lose it, that will induce a vacuum event. Or you can have a real vacuum from the properties of your source. And to warranty that we were looking at the vacuum from our source, we implemented this scheme for zero photon subtraction to increase the probabilities of vacuum. And in a minute, you will actually see, probably the next plot that I will show will clarify this point. So what we did is we studied the degree of coherence, but for these subsystems. And if you take a look to the vacuum, so this is arm 2, this is arm 1. So the vacuum is a little bit higher than the theory. And the reason for that is because we have the vacuum from the thermal source, but we also have just the absence of events. And in practice, we cannot discriminate one from the other. But what we were able to do is to increase the probabilities of observing vacuum from the source. And that's why, even though there is a small difference between theory and experiment, it's actually very similar. For example, for 30 degrees, this is the experimental vacuum, and this is the theory. And then for 45 degrees, we get this experimental vacuum, and this is the theory. So this is always higher because for the reasons that I just gave, and similar here. I'm not sure if that answers your question about the vacuum.
Yes, but what is that vacuum pre-selection? I mean, how do we ensure that it is zero state? Like, what is the vacuum pre-selection?
What is what? I mean,
Vacuum pre-selection. What is the vacuum pre-selection?
what is the
What
vacuum
condition?
pre-selection? Yes. So the way
How
you
do we ensure about that vacuum pre-selection?
right, the way you go from these probabilities of observing the vacuum to that is when you pre-select and post-select on the vacuum, that means that here you have vacuum. So in your input, you have vacuum. If you have vacuum here, then your chances of getting vacuum here increase. But if in addition to that, you may just force these two detectors to see the vacuum, and then you correlate these three detectors and you force them to see the vacuum, you dramatically increase the probability of measuring the vacuum from 7% or 8% to 82%. And that's basically the point of this scheme for zero photon subtraction.
So are you using some pulse laser and the time being of that to pre-select the vacuum or something?
No. Everything is continuous. So what we're doing in this experiment is just we do binning. So we basically define, let's say, a wave packet within the coherence time of our source. And then we make sure that within that coherence time, there is no vacuum or there is no multi-particle event. It's just empty.
Okay.
And then
And that time binning is continuous, right? I mean, you can't. Okay.
Yeah. So this is how this is why actually we obtain these high probabilities of observing the vacuum. And this is not described in the paper, but this is just ongoing research. So one of the things that we discuss here is that these vacuum plasmons were generated by the vacuum fluctuations of the thermal field. And that's connected with other interesting dynamics, for example, with Casimir effects and all these things that we did not discuss in the paper, but we're working on that. And actually, I will go back to this vacuum dynamics for imaging. Actually, that plays an interesting role. I will just describe it. Okay, so when I was starting my presentation, I told you that plasmons result from the coupling of photons to electrons. And as you know, photons are bosons and electrons are fermions. And actually people like Alan Aspect has, in the past, he studied bosonic and fermionic Hamburg-Brown and twist effect, just using a different isotope. I forgot the atom that he was using, but the point is that he was saying that bosons will show like a G2 above 1, and then fermions will show like a G2 below 1. Here, when we separate the multiphoton subsystems, we have some multiphoton subsystems that show a degree of coherence below 1, and some others that show degrees of a degree of coherence above 1. And what we now study is that depending on the value of the degree of coherence, we will observe like a bosonic or fermionic interaction. For example, first, what we did is we just, let me go back a little bit. So we have two detectors here. So what we did is we scanned this detector, and the first thing we did is we just placed this at 0. So we just define a position of 0, and then we scan the other detector. For the vacuum, when we post-select on the vacuum, so what we see is that actually, even though vacuum is like super quantum, right? That's a signature of quantum. When we correlate the vacuum, we see something that looks classical. I mean, this looks just like single photon detection. We see peaks. And in this case, we see the peak center at 0 because one of the detectors, so the detector K2 was placed at 0, and then we scan K1. And as we increase the strength of the plasmonic field, we see that the visibility also increased for the correlation. But then when we, for example, correlate a 7-particle subsystem with the vacuum, we see that we measure the opposite. Now you will see a dip where you have a peak, and same thing here, and same thing here. And in this case, the degree of coherence is below 1. Here, the degree of coherence is above 1. And interestingly, when you displace your second detector, so now we call K2, now we put it at minus 0.43 millimeters. If you have a bosonic system, as I was showing it, the degree of coherence should be above 1. So it should be above 1. And then this will be a correlated system. And if this is a correlated system, you will see a peak at the same position of your detector. So when you scan K1, you see the peak or the maximum at the position where you put the other detector. Now, if you post-select on a subsystem that have very weak correlations. For example, this 9-particle system, the degree of coherence is close to 1. And in this case, we lost correlations. So in this case, the peak was here, but in this case, the peak goes to 0. So we just call it an uncorrelated system. But interestingly, when we pick one of the subsystems with a degree of coherence below 1, we see anti-correlated systems. Now the peak is centered at positive 0.43. Again, so we place the second detector at this position. But just because the system is actually uncorrelated, we see the peak in the opposite direction. And then we attribute that to fermionic coherence, just like in the paper of Aspen. Okay, here I'm just showing these dynamics. So this is a little bit understanding how the multiphoton subsystems behave. And what I will show you now is how this can be used to build technologies or to do imaging. So one of, so, oops. Okay, so with this, I mean, with basically what I told you, probably you are all familiar with this illustration that shows that we have a quantum and a classical world. And then there is like a line or like there is a line. And then if you pass this line, you're in one part. If you pass the other line, you are in the other part. And then, for example, people attributes when people are using entangled photons, they say, well, I'm in the quantum world. I have entangled photons, and then everything I will do, if I don't have losses or anything, will stay quantum. So I will live here. And then people typically think that if you have a laser, a classical laser, then you can use Maxwell equations to describe everything that you will see, then you live in the classical world. So it seems like what I just told you does not agree with this cartoon, because in the previous experiment, we started with a classical beam, a thermal beam, and I even measured the degree of coherence, and that was classical. And then I end up isolating subsystems, and then this subsystem shows something different. So what this means is that you can start with a classical field, and then you might be able to extract quantumness from that classical field. And then that will be very convenient because classical light sources are brighter than quantum light sources. And this takes me to the next topic. Well, based on what I just said, then you might be asking, can I do quantum optics using classical light? We believe that the answer is yes. So actually the title of the paper that I briefly presented is called Non-Classical Near-Field Dynamics of Surface Plasmons. Surface plasmons are in general, are understood as classical waves. And then I'm saying that we're studying the non-classical dynamics of that. When we published this paper, that was highlighted also in Nature Physics News and Views. And if you see the title of the highlights, they say that, well, one can do quantum statistics from classical light. And then he discusses that if you do that, then you can build probably more robust quantum technologies. And well, I will just tell you the implications for quantum technologies. So a few years ago, Photonics Spectra interviewed me and to talk about quantum imaging. And as you may know, quantum imaging is very interesting because you can use non-local effects to create images with unique levels of noise. And you can use also that for super resolution. So it's a very nice and very active field, and I've been working on this field for multiple years. And as I say, I mean, quantum imaging is very interesting, but unfortunately is very fragile. So if you turn on the light, you will have more background light than your signal, and you won't be able to do anything. And I just said, because we're working on this kind of effects, that maybe one can just implement projective measurements and then isolate subsystems and do or demonstrate a more robust quantum imaging scheme. And this is basically what we did. So this is our paper. So it's under review, but you can find it in the archive. And one of the, I think that we make two strong claims. So the first is that we say that we use conditional measurements to extract quantum features of thermal photons. So we start with a classical source of light, thermal light, and then we'll use the same tricks we used before to extract quantum systems. And what we found is that these quantum systems show better signal to noise ratios, and that's useful. Then the second claim that we do is that it's seen just like in the review paper or in the news and views paper, we believe that if it's possible to combine natural light with non-classical detection, then that might be an interesting path to develop robust quantum technologies. And this is what I'm going to describe now. So very briefly, let me remind you, the field of quantum imaging initiated with this experiment also by Pittman and Jan Shi and others. So here they start with a laser, they produce entangled photons. These photons are anti-correlated in momentum, but they are correlated in position. And so they split signal and idler, and then they use, let's say, signal to illuminate an object. And then they detect these photons with a bucket detector that does not have any spatial resolution or anything. And they use that to get another detector. And back then they didn't have cameras, so they did raster scanning. And they saw that the image of this object was actually formed here. Then Miles wrote this very nice review later, and then he just shows that if you use this bucket detector to get a camera, like an ICCD or like an EMCCD, then the image of your object will appear here, and that's known as ghost imaging. That's old, but people keep using it. And then these ideas were also used, for example, to get subchat noise limited quantum imaging. People use that for super resolving quantum imaging. And then, I mean, these non-classical correlations can also be used for secure quantum imaging. All these techniques are nice, but as I said, they are very fragile. If you turn on the light there, then everything will be gone. And that's an issue because even though they are very cool, it's hard to use them in realistic application. One of the things that you should see is that even if you check quantum imaging, most of the techniques rely on a quantum source. And by that, I mean, for example, you can have single photon sources, you can have SPDC sources, or you can have more complicated sources. In our case, we don't use that, and we still do quantum imaging. So we start with a natural source of light. In our case, just like in the previous experiment, we start with thermal light, and thermal light is just like, let's say, sunlight under some conditions. Then we use that light to illuminate an object. And then here, you could use a photon-number-resolving camera, but that doesn't exist. Well, Hamamatsu just released one. We haven't tried it, but it might work or not. But anyway, so we didn't have one. So what we did is we used compressive sensing to build a camera. So here we have a DMD. So we image the object onto the DMD. Then we collect light, and then we just have a fiber coupler. We have two arms. And then we use this technique, this part, to build a photon-number-resolving camera. And then, well, this is the object, and this is our source. So just like in the previous case, if we go and measure the joint photon number distribution, we will see something like that. In this case, we were interested in doing this with only few photons. So I forgot the mean photon number of the source, but that's reported in the paper. And this is the UN photon number distribution. If you reconstruct the object under these conditions, then you won't be able to get anything, because so we ran this experiment with very weak signals. So what you get using classical compressive sensing, it's something like that. Here you cannot see the object because the level of noise and the level of your signal is comparable. So it's really hard to see your object. But what we do is when we project this system onto, let's say onto the vacuum, we see something. Then if we pick one photon subsystems, we see something. And then if we pick 6, we see something. So these are quantum images that actually were extracted from the classical image. So let me just explain very briefly how compressive sensing works. So we have an object, and then we image this object onto a digital micrometer device. And then here we project random matrices that we will call A. And then what we do is that for each of these random matrices, we measure intensity. This is classical. And then each measurement of intensity is an element in the vector Y, such that we can write this problem like this. So this is our object, then this is projected onto the sensing matrices, and then we have one element. If we perform all the number of, if we perform 100% of the measurement or all the measurements in this matrix, we can just invert. If you have this and you have that, you can invert this matrix and then get the object. But the cool thing about compressive sensing is that you can reduce the measurements and then you just use optimization to retrieve the object. And what you get is what I call O prime. And O prime is just an approximated version of your object here. And you get that by solving this optimization problem. So again, what you have from your experiment are these intensity measurements. So you have this vector, you know the random sensing matrices. So you also have the matrix A. And then you solve this problem and you get O prime. So this is, and people have been using compressive sensing for classical applications and all that. Okay, what else? What's the other important piece of information? Well, the other part is that we're using quantum statistics, and we start with a classical source of light. So what we do is we use the Glover-Sudarshan p-function representation, and probably you know this, but if you have a coherent beam, then the p-function for that can be written like that. If you have a thermal beam, then your p-function is expressed like that. Recently, well, I didn't mention that. So you can, if you just want to get the density matrix for a source that is produced by the combination of coherent and thermal, you can just use Glover and Sudarshan and then you have it. If you want to add another degree of freedom, let's say you are interested in the excitation mode of the field, but you also care about the spatial profile, then you can check our paper. So this basically incorporates additional degrees of freedom. So if you want to learn more, it's also in the archive. So if you have a contribution, let's say from coherent and thermal, and these
Okay,
sources are, yeah.
Omar, you have 5 minutes.
Oh, okay. So, okay, let's say if you have a combination of coherent and thermal, you can just calculate, and if these sources are indistinguishable, you can just calculate the general p-function through convolutions. If you have the p-function, you can get the density matrix. If you have the density matrix, you can describe the UN photon number distribution like here. In our case, we took into account the efficiencies of our detectors and the noise and dark count. So that's also integrated. If you do all that, you can describe this UN photon number distribution. But let me move quick. So when we just did the experiment classically using compressive sensing, our signal was so weak that we didn't see anything. Then we project onto the vacuum and we saw something. Then we project onto 3-photon subsystem. We improve the quality of the image, and same for this 7-photon subsystem. So probably this is obvious, but if you add V to C to B, if you see B and C are almost opposite, then you will get basically the classical one. You won't be able to see this. Yeah, so you won't be able to see that. And one of the nice things is that the signal to noise ratio for the post-selected images increase exponentially. So that comes from the theory. And then, we prove it experimentally. So in case, if you're asking why this works, I think that, well, based on what I just said, it makes sense. So if you see here, the background is yellow, and here the signal is yellow. So you add this plus that, you will get flat. But then what this means is that actually the noise is distributed in some of these subsystems. For example, if we post-select on a 4-particle subsystem, something that it's uncorrelated because it's close to 1, you don't see the image. But then if you post-select, let's say, on a quantum subsystem with a degree of coherence below 1, you get really good contrast. And why is that? Because probably the noise is centered around these 4-particle systems. And there is not a lot of noise in this system. So you are basically filtering noise. So we extended this protocol to demonstrate photon subtraction really quick. Let's say that you have a thermal field. So thermal field, as I just showed, contains more vacuum. So that's the most prominent term. So you will get 1 photon, then vacuum, vacuum, then 2 photons, then vacuum. If you calculate the mean photon number, well, naively, you can just add them, and then the mean photon number will be 0.6. Now, if I subtract photons using this beam splitter, and now I only measure photons here every time I detect a photon here, basically by doing that, I'm rejecting the vacuum. So I'm killing the vacuum, and I can change the photon statistics to something like that. At the same time, I will be increasing the mean photon number. And we use that for our case. Again, in the classical case, you don't see anything. But when you subtract 1 photon, you see something. And then we run this experiment at even lower intensities. So when you subtract 2 photons, you see the object. When you subtract 3 photons, you see something better. And as you can see here, the G2 changes. It goes from thermal to almost coherent. And the mean photon number changes, and that allows you to increase the signal to noise ratio. In this case, the improvement that you get is not exponential, it's linear. And then each of these lines here represent the number of measurements implemented using compressive sensing. And this is with respect to the raster scanning. If you take all the data, then your signal will be good and you get better signal to noise ratio. But even if you take a fraction of measurement, let's say 25% of the measurements, you can still get an increase in the signal to noise ratio as you subtract more photons. And with that, I'm done. And what I just showed you is that we demonstrated a single pixel camera with photon-number-resolving capabilities. We also extract quantum images from classical images. I show you that depending on how you post-select, you can get exponential enhancement. I also show you that you can do imaging with the vacuum fluctuations, which I found interesting. And probably the most important is that you can combine natural light sources with non-classical detection to develop more robust quantum technologies, like in this case. And then with that, I'm done. Thank you.
Okay, so thank you, Omar. This was a fantastic presentation and perfect timing. And again, congratulations on many excellent results. Okay,
Thanks.
so we are open to questions now.
I have a question, Anand.
Yeah.
So, uh, so if you please, Omar, if you please go to slide number 31 to 34, means that where you are.
31, there you go.
Yeah. Yes, correct. So where you are extracting that images from the classical using the classical light. So here we see that when you are imaging the means simple imaging with classical light, you are not able to extract the object. So what kind of object it is? Is it something, some phase object or some mask or some?
No, this is just an amplitude object. So we just in the experiment we project the object on a digital micrometer device, but you can equally do it just with an aperture or something like that.
Okay. And light, the natural light intensity is pretty low. That means noise is means overshooting, and you are not getting image of that. But when you go for this projective measurement in the number basis, and you are able to get it. So is it something like a noise also has some number distribution, and somehow you are going to post-select that part? Means what
Yeah.
kind of things is happening here?
That's, yeah, in addition to this vacuum and the multiphoton subsystem, what this is actually telling you is that maybe the noise is concentrated here. Let's assume, as you said, the noise has a distribution.
Yeah.
And probably that distribution will be centered here. When you do the whole thing, that noise forbids you to see the image, but probably if you ignore this part, you say, well, I don't care about that, and I will just measure X, then the amount of X from the noise is lower than the amount of X from your signal. And that's why you can see the image, because the noise is also distributed in one particular part.
And for the thermal source you are using, is that means that also has some distribution of that thermal source has some means engineered thermal source you are using or something, means is that engineering that thermal source also has some impact on uh, reducing this noise part or something?
Uh, I think it does. It has an important role. For example, this is something that we haven't explored, but I was recently talking to the students and thinking that maybe even super thermal might help. Let's say that you replace your sunlight that has, or let's say that you replace a thermal light with a G2 of 2 to something that is super thermal and has a G2 of 5, let's say. Then I think that this will improve the performance of this technique, but we haven't tried it. It's just me guessing. Because in this case, and the reason why I believe that is because now the level of fluctuations and all that will be substantially different, right? So if you compare the noise, let's say in this case, we have the noise from the lab, right? We have sources of light, and then we just made the noise comparable to the signal. But now if your signal fluctuates very differently, and if this is super thermal light, I think that it will be easier to discriminate one from the other. And then you should be able to get better images or to extract better images. But we haven't done it. So this is just me guessing.
Yeah, one last question I have, that means how you are deciding that means you for imaging you should you should use that conditional measurement of like 6 or 4 or something, or sometimes 2 6. Means is it some way or algorithm to find out which combination will give you the best image or something from for extracting that image?
Yeah, so no, I mean, in this case, we have a theory that describes all the features that we're observing. So actually, if you see, this is the theory. But if you just want me to tell you, let's say the recipe, at least with the understanding that we have right now, I will say that if you want to get the best images out of here, you pick the subsystems that are very strongly correlated.
I see.
Example, you pick this, and that's why I believe that super thermal will give you good results, because you can pick something with a really high G2 that will be very strongly correlated and that gives you good image. So your other option will be to pick something closer to here, and that will be very strongly anti-correlated. And for example, for that, we have E. But then if you pick something in the middle that will be weakly correlated or uncorrelated, just like in the plasmonic case that I show, then you don't get anything. And here we have two possibilities. One is that the noise is actually localized around this system, and actually because the noise is localized there, your correlations are weaker. That we think that that's what's going on. But yeah, so I don't think that we need like an algorithm or anything. So if you just want a short answer, I will say go and pick those strongly correlated subsystems or those strongly anti-correlated subsystems. That will give you the image.
Thank you very much.
Yeah, thanks. Thanks for the question. Yeah.
Okay. Other questions? Okay. I have a few. Sorry. Yeah. Go ahead, Neelakshi. You have a question?
Yes, in this figure itself, the pink plane is like dividing somehow the classical part and quantum part. So how that 1 G2 equal to 1, like in that figure itself, 32, slide number 32. Yes, this degree of coherence versus R1, R2. So here, like how why less than 1 is quantum and classical? How we are differentiating between the classical and quantum?
Oh, well, there are multiple ways in which you can do that. For example, Fock states, or let's go to single photon sources. So if you go and measure the G2 for a single photon source, your G2 will be below 1, right? And that will be for something closer to a Fock state, and that's why people use Fock state for metrology, because in theory, Fock states, if everything is ideal, will allow you to beat the chat noise, right? So then every time you do an experiment and you have a G2 below 1, you say that you have sub-chat noise systems, and then you can get quantum enhancement. Here we have the same thing. We have just subsystems that have a degree of coherence below 1, and then you can say that the noise associated with that system is weaker or is below the chat noise, and then that should give you a decent signal. That's one way. Here, for example, this subsystem or super thermal light, it's like very classical light, but the degree of coherence is actually very high. That's because the fluctuations are very strong, and you can use these these fluctuations are correlated, so you can use the correlations of intensity fluctuations to also do things even in the presence of noise. So here you have two options. You can go classical but strongly correlated, or you can go quantum. And then if you go quantum, the noise associated with or related to this subsystem will be relatively small.
Okay, so can we somehow connect this with the Wigner negativity and those things also?
Yep. So after, for example, you have this 3-photon system, or let's say here you have this 1-photon system. What you did with this projective measurement is you start with a wave function that is classical, and then you project it, or you collapse that wave function into a Fock state. And you know that the Wigner distribution for the Fock state is negative, and that means that this is a non-classical state of light. And this is why we actually say that we can do quantum imaging from a classical source, because once you project your system into a 1-photon system, then it's quantum, and the Wigner distribution is negative.
Okay. Okay. So I have one more question sometimes you are doing like we are doing here the three projection, sometimes 7 7. So and so on. So all these multiphoton events, whatever it is 3 3 or 7 7, the probability of getting 3 3 or 7 7 should not be the same, right? So like the probability of observing these events also will affect the measurement, right?
Yes, yes. So if yeah, if we consider this joint photon number distribution, and let's say for this case, in our case, in this case, the level of your signal and the level of the noise is comparable. What that actually means is that let's say the photon number distribution for the noise should be, let's say, in this region. That's why you cannot see the image. However, if you go and measure 10 photon events, probably you will see the signal, or this subsystem will have less noise here. And that's fine, that will give you an image, but if you see, your probabilities of getting 10 photons is pretty low. So you have to wait, and you have to wait until you get enough repetitions. That's the bad thing. So if you want, for example, here, 6 gives you a very nice image, but to get 6, you have to wait, right? I mean, most of the time you will get the vacuum. Then you will get 1s, 2s, 3s, 4s, and this will be like a negative exponential. So yes, so just like in a spontaneous parametric down conversion, if you want to get a higher order generation, you just have to wait. You will get it, but you need to be patient.
10 10 will give even more nicer image, but we need to wait for longer. Is this like that?
Right. But the good thing is that it's quite probable that you won't have noise there, right? So yeah.
So I have one last question. That is, it is mentioned that there is showed that what is quantum Gaussian shell model in the slide 29, I think. Uh,
Yes.
I mean, what is quantum in the Gaussian shell model? That I did not get. Gaussian shell model is Gaussian shell model. So what is quantum Gaussian shell model?
Right. Basically, the quantum part from our paper is that we propose a Gaussian shell model, but the quantum part is that we can write a density matrix, and then from the density matrix, we can just do projective measurements. So for example, if you have the classical Gaussian shell model, that might allow you to describe spatial coherence, right? So you will be able to describe spatial coherence. So our model allows you to do that, but in addition, it allows you, for example, to describe the spatial coherence of a quantum subsystem in a partially coherent light beam.
Okay. All right. Okay. Thank you.
Yeah.
Okay, other questions? Okay, I maybe have two quick questions. In the very beginning of your talk, Omar, you mentioned something like multi-port beam splitters or something, right? So do you know of any implementation of multi-port beam splitter, not just theory, but experimentally?
Well, we did this experiment, this paper here that you see is an experiment.
Mm-hmm.
But everything that was done here was with single photons. So we just study single particle dynamics.
So I mean, is this probabilistic, and how good it is? In any idea?
Yeah, everything is probabilistic. So we use heralding. So we have an SPDC source. We measure one, and then with the signal from that detection, we trigger an ICCD, and that's how we did these measurements.
Okay. Okay.
Yeah.
The other question I have is regarding the last part of your talk. So in that imaging, I think this Suman was also asking the same question. So the improvement of signal to noise when you have the higher number state, first of all, what kind of noise do you have here? And the second is I mean, is this correct that is this a correct intuitive understanding that the kind of correlation you have in your thermal source in the higher number state, the noise doesn't have that kind of correlation in the higher number state. And that's why the SNR keeps on improving as you go on the higher number state. Is that correct?
Is that correct? Yeah, that's correct. Yes. Yeah.
And what is the kind of sources of noise you were kind of using here?
Here we just run the experiment like basically just getting contributions from light sources in the lab. So we had the monitor on, we had some light from the room. And we just what we did is we attenuate the signal to a comparable level to this noise. And the way we did that is well, first we did the reconstruction, we get classically a nice image. Then we say, well, we can easily see the signal. Then we attenuate the signal a little bit. And then we attenuate it a little bit until we were not able to get any reconstruction. And then we say, okay, fine. At this point, we're not getting any reconstruction because the amount of noise and signal are comparable. And then we just started from there. And then we start extracting the subsystems. Yeah.
But if source is thermal and noise is also thermal, I mean, even though these two sources are, let's say, independent, but the correlation should be same as far as noise. I mean, no noise just meaning noise source and signal meaning, the thermal source that you are attributing or making it to be a source. But the correlation in the higher number state, that should be very similar, isn't it?
Yes and no. Because, well, here, yes, because we're running an experiment, so we designed the experimental conditions. So in the paper, we have one thermal mode. Basically, what we have is our rotating ground glass, and then we just have one mode. And then the G2 for one mode is actually 2. But if you have multiple thermal sources, then you have basically a multi-mode thermal source. And as you increase the number of modes in your thermal source, then your G2 approaches 1.
Okay.
So
the photon statistics of the signal has to be different than the photon statistics of the noise. And that's when you can actually extract it, right?
Right. Yes.
Okay.
Yeah.
Makes sense. Okay. Also, I mean, this is very nice work, really fantastic. But now that you are able to kind of detect these higher photon number kind of Fox state, is there any possibility also of improving the resolution? This is just improving kind of extracting the signal from noise, but can you just improve the resolution also in absolute sense?
Yes, actually, we did it in this paper. So, well, I have to say that it's not. Well, in this paper, we combine quantum statistics with machine learning to improve the resolution. So, but I mean, the fundamental physics resides on the quantum statistics of the sources. So probably you're familiar, like what people have been doing, like almost everybody, is to achieve super resolution, they decompose an image into like a complete set of bases, right? For example, you can use LG modes or HG modes, and they have been, I mean, that technique works. I mean, there are multiple papers are around that. The problem with that is that if you do this, then you have like practical limitation. For example, then your imaging system is quite sensitive to centering, for example, because if everything is not perfectly centered, you cannot do the projection that you need and you cannot extract information. So However, photon statistics are not limited by diffraction. I mean, you will get the same statistics even if the system is shifted. So we say, well, instead of implementing the projections on spatial modes, we will project onto, or we will measure the statistics, and we will just extract information using statistics, and then with that, we develop a theoretical model for the statistics, and we use that to train a neural network. And then we combine both, and we actually we were able to do super resolution. Actually, I have an image here. Probably the reference is not great, but this is, there you go. So this is a more recent paper, but these images come from the NPJ paper. So here we have three sources that you cannot identify. So this is actually the experiment. And we just call it diffraction limited imaging. But then after using statistics and then machine learning, we were able to identify that there were actually three sources. So these are the three sources.
I see.
So we went from this distribution to this distribution.
Okay, well, maybe a quick follow-up. Like, we see this resolution enhancement, and the major where you kind of go super resolution, Heisenberg limit, and so on, is when you use this entangled noon state, right? I mean, in an absolute sense. Now, what you just said and what you have presented is that the signal noise enhancement is because the imaging is based on photon statistics rather than just intensity. Now the question is, can you, I mean, since this is projection based, so can you extract, or is it possible to extract noon state out of thermal state, and so that you can enhance the resolution?
Well, that's a very interesting question, and we're working on that. I mean, actually, the question that we're trying to answer is a little bit more general. So we were just mentioning this Gaussian shell model. And I told you that the difference with respect to, for example, the regular Glover-Sudarshan function is that this approach allows us to take into account the excitation mode of the field, so the photon number, basically. And you can also add or incorporate an additional degree of freedom, let's say the spatial profile. And you can have, you can reconstruct a density matrix that depends on the excitation mode of the field, and also depends on, let's say, the spatial properties of your beam. We have that. Then what we know is that, I mean, here in what I just showed you, we have been extracted multiphoton subsystems, and that's fine. You can do that. But then the question that we're trying to answer is now, let's say that you project onto an entangled state, as you said, let's say onto n equals to noon state. So what we know for sure is that the dot product between the n equals to noon state and the density matrix of this sophisticated system with multiple degrees of freedom won't be zero. And what that means is that there must be some noon states encoded in this macroscopic system. But will that be enough to claim that you have entanglement? We don't know, because you will have to define, probably to use one of these inequalities, right? And to say, well, I violate this inequality with my extracted systems. And we haven't done that. We're working on that. And we don't know the answer, but yeah. But what we know is that the dot product shouldn't be zero. I don't know if that's enough to say that, sure, you will be able to extract also entanglement. We don't know, but that's an interesting.
Well, if you had, or if one has a perfect number resolving detector, right, then that dot product can go to zero. I mean, in the sense of post-selection. But I think the most number resolving detector right now, I mean, there are very few people who have access to, the better ones, is like if the detector gets 6, it also has the possibility of detecting, 7 or 5 with a very similar probability. So that will ensure that you probably don't have the dot product that you're talking about. That dot product in this scenario cannot be zero. Is that correct?
Well, that's correct. But here, just like in the classical Gaussian shell model, well, we are considering partially coherent like fields.
Mhm.
And in this case, we mean partially coherent in the sense of photon number as well. So we mean something between a beam of light with a G2 between 1 and 2, let's say 1.5. Then that beam of light will have partial correlations even in the photon number, even if you have a perfect PNR.
Okay. Okay.
So yeah, I mean, well, you know this, right? I mean, you have a lot of experience with entangled photons. In entangled photons, in principle, you have perfect point-to-point correlations, right? But for example, you can have partial correlations if you use thermal light. I mean, let's say this point will be strongly correlated with this point, but then if you pick another point here, that will be partially correlated with this point. Yes, so then if you, just because we are considering partially coherent, like there will always be these partial correlations, even if you have like a perfect detection scheme.
I see. Okay.
Yeah, actually, I mean, probably we're all familiar with the Henry Brown and Twist experiment, right? That the correlations go from 1 to 2, and then you have everything in the middle, and that means that you also have partially correlations, right, at 2 different positions.
Yes.
And you have that in time, and you also have that in space, and you have it in different degrees of freedom.
Yes. Yes.